Hi, what I have here on the workbench today is a Micsig STO1004 100 MHz bandwidth 1 gig samples per second 4-channel digital storage oscilloscope. Selig provided me this unit for a review. I will leave a product link in the video description below, along with a link to all the Micsig products Selig currently carries. If you are interested after watching this video, please be sure to check it out. I have heard a lot of good things about Micsig's Smart Series tablet oscilloscopes, and I believe the STO in the model name stands for Smart Tablet Oscilloscope. I remembered watching one of Mike Electronic Stuff's review video of an early version of Micsig's STO series a few years ago, and was quite impressed by its performance. So as you'd imagine, I'm very excited to get my hands on an updated version of the STO1004. The reason it is called a tablet oscilloscope is not just because it takes the form of a tablet computer. This oscilloscope actually operates on Android operating system. As you will see in a minute, using a commercial operating system instead of rolling your own makes a lot of sense. This allows manufacturers to concentrate on the application itself, create better quality software, and lower the overall R&D cost. The STO1004 has some quite impressive specs. For instance, it has an input sensitivity of 1 mV per division instead of the standard 2 mV per division for a ×1 probe found in other oscilloscopes. It offers very fast waveform update rate at 130,000 waveforms per second according to the spec, and has a memory depth of 70 megapoints. It also has intensity grading display, which is something you typically only find in high-end oscilloscopes. This scope also has very sophisticated triggering capability and can decode many common protocols. The best part is that the STO1004 can be battery powered, and the claimed battery life is around 5 hours. This makes it very useful for field operations such as in the automotive industry for diagnostics. Of course, all of these advanced capabilities came at a cost. The scope is currently priced at just below $700, far more than your usual entry-level scopes. But this scope is not positioned as an entry-level scope, as the features it offers compete directly against many high-end scopes from name-brand manufacturers. So this scope is actually at a bargain price given its market positioning and capabilities. Before I power it on, let me quickly point out a few things. The overall dimension of this scope is roughly at 10 inches by 7 inches and 1 3/4 inches in depth. It has an 8-inch LCD that supports a resolution of 800 by 600. On one side, you have this strap that you can see. This is used for you to carry the scope while you are in field operations. Now, one thing to keep in mind is that this scope is really heavy, coming at about 4 pounds. So you probably don't want to use it for a prolonged period of time using just one hand. On the side you can see we have a power button, which is a soft button. However, there is a physical button at the bottom here. You will have to turn it on before you can operate the scope. This is an excellent touch in my opinion, as not only you can prevent the scope accidentally being turned on during shipment, but also when you are not using the scope for a prolonged period of time, you can use this to preserve the battery, as there's always going to be some parasitic power draw when the unit is softly powered off. Underneath the power button, we have a grounding connection point. Obviously, as a portable oscilloscope, one of the advantages is that you can operate it in floating configuration, and most of the people using the scope will probably not bother with grounding. But if you are doing some sensitive measurement requiring grounding to reduce noise, you have the option to do so. Next, we have a USB connector for an external mouse, which I will show you once I power it on. By the way, you can also hook up an external keyboard using the same port as well if you really want to. And underneath this USB port, we have another USB port for your connectivity to the PC. We also have an HDMI output port which mirrors the output on the oscilloscope. And we also have a USB-C port. When connected to a PC, it will show up as a removable drive, and you can transfer files back and forth. However, the USB-C port is only limited to exchange files with your computer for data links, and you cannot use it to charge the battery or power the scope, which is really a pity. And here is the interlocking power switch that we mentioned earlier. Underneath here, we have a power jack for the 12 volts that you can use the supplied power adapter to power the scope. On the top of the scope, we have 5 BNC connectors. 4 of them are the 4-channel inputs, and these came with Micsig's UPI, or Universal Probe Interface, which provides power through the interface and it can also interchange data with the connected probes if the probes support that protocol. Note that these connectors are Cat 1 rated, so it's meant mainly for electronics and not industrial electrical work. And here's a view of the back of the scope. Here we have 2 stands. They can be pulled out so the scope can stand up. Now they do a pretty good job for supporting the scope. And here we have a single fan. This fan is operating relatively quietly, so it's not an issue. And here is our battery compartment, which houses the 7.4 volt battery here. Let me power it on while I'm talking, as it does take some time for the scope to power up. Now, the surface of the LCD is glossy. I personally don't mind glossy LCD screens, but they are not very easy to work with when making videos, as things in the background would show up as reflections, which make it quite distracting. Luckily, the STO1004 does come with a screen protector, which has a matte finish. Unfortunately, the screen protector is not very easy to put on, as it is ever so slightly wider than the screen, which I didn't notice when I tried to put it on first. So I had to lift the side once I realized that it was not going to stick, and had to trim the side freehand with scissors. So if you look at the side carefully, you will see that they are not quite straight. And I'm by no means a pro for putting on screen protectors. As you can see, there are quite a few bubbles trapped in. Anyway, the matte finish of the screen protector should make it much easier for you to see. That is why I wanted to put it on initially. So it took roughly 38 seconds to boot up. This is not speedy by any means, but it is well within expectation as it uses a commercial Android operating system, and the performance is largely on par with many of the modern instruments. Powering off is much quicker. All you need to do is medium press the power button, and this menu will pop up. You can either shut it down or reboot. Powering off only takes a second or two, so it is not an issue at all. Now, the power button actually has many functions, depends on how you press it. If you just press it quickly, it will go to this application page. And if you press it medium, hold it, it will actually show you the power on and power off function like what we saw earlier. And if you just keep holding it, it will eventually power off the unit. So let me just show you the power off, and you will see it is really fast. Because it's a 4-channel scope, it also comes with 4 sets of these probes. These are your P100 probes, which are fairly standard. And this is obviously Micsig branded. It also has a fixed attenuation at times 10. There's no way for you to switch to time 1. But that's actually not a problem at all. The compensation is at the head itself, and it also has a ground pin here that is interfacing that universal probe interface. Now, the probe, obviously you can take the tip off and put a grounding clip here to measure some high frequency signals to reduce the impedance of the probe tip. And also you can remove the grounding clip as well. So these are fairly standard, but they do feel like a very high quality probes, and you get 4 of these. Let me plug in the probe here, and we will take a look at the test signal and take a quick look here. Now let me do a auto acquire. You'll see that we got that test signal right away, so that auto acquisition is very fast. And by the way, my goal is to show you some of the important stuff in this video, so the video won't be too long. It is always hard to strike a balance when making oscilloscope review videos. So if there's something I didn't end up showing and you wanted to see, please leave me a comment below. If there's enough interest, I will make a separate video to address those specific requests. Compared to the Plus models, this model did away with those adjustment knobs. Personally, I do like these joystick-style multifunctional buttons, as you can do 5 adjustments with just a single button. You can do up and down, left and right, and you can press the button as well. So there are 5 different functionalities with a single button. So with this arrangement, I think it simplifies the user interface and make the scope more portable. As right now you can see that none of these controls are actually sticking out like those knobs. So this definitely prevents you accidentally bump into those knobs and damage the scope in the process, making it more portable. After having played with the scope for a few days, I can say that they really did the user interface very well. In fact, I think they nailed it. And giving the different sets of controls controlling the same functionality, you have a lot of options when you are in the field. The controls are so intuitive, you don't need to read the manual in depth before you can figure out how to use this scope. Let me just quickly demonstrate a few things here. Obviously, I'm only going to be scratching the surface. If you really want to explore the scope, you will just have to play with it and figure it out yourself. So for instance, the first thing is you can obviously use the buttons here to adjust the time base and to adjust the attenuation. That is something fairly intuitive. And also you can do the same thing obviously with the buttons here. So these are some of the essentially the same functionalities. You can either use a touch screen or you can use the controls on the side. Of course, later I will show you a little bit using a mouse to operate the same user interface. And to adjust your input, you can just swipe out the channel and you can see we have AC coupling, DC coupling, so on and so forth. You can change your attenuation right here as well. So all these are very intuitive. To access the main menu, all you do is swipe from top down. You will see here we have all the commonly used functions right under your fingertip. You can choose measure and you can choose save, sample, display, trigger, auto, and reset everything. Now, the trigger functionality, again, there's a lot in this triggering capability here. You can see that you can choose the common triggering, edge triggering, pulse triggering, logic, and so on and so forth. So there's a bunch of things. Depends on your application, you can adjust your triggers accordingly. In our edge triggering, for example, you can choose falling edge, rising edge, and AC coupling, DC coupling, so on and so forth. So that is a fairly common stuff. And while I was poking around, you probably noticed just how responsive the UI actually is. So this is clearly very well engineered. Now, of course, I can turn on the counter on channel 1, so you will see that we have the display frequency read out. The measurement on this scope is also very easy to use. You can swipe it up. You can see that we can turn on all the measurements. You will see all the measurement displayed on the bottom. If you don't want this, you can turn them off. Now, another thing is the cursor measurement. You can see we have 2 of these dedicated buttons here. So if you press, let's say, the vertical button, you will be able to see the 2 cursor lines. You can use them manually, adjust the cursor, and you can read out what the delta is. Similarly, you can use the horizontal cursors, and that also serves the same purpose. You can see that it's very easy to use. Now, you can also use the fine adjustment so that, for instance, you can do some very fine placement of the cursor. Now, you can notice that right now the cursor moves much slower than it did before when I turned off the fine adjustment. So this is something that you can use to further adjust your cursor positions. Now I just plugged in a wireless mouse. Of course, you can also use a wired mouse instead. And you can see the mouse cursor on the screen here. Now, you operate the mouse exactly as you would with your finger. For instance, we can kind of click and drag this vertical cursor here, and you get an idea. Also, you can, for instance, drag the menu item from the side out, and you have access to all the same menu items as you would with the touch interface. So this is a very clean design. You don't have the different type of behavior with the mouse or with your finger. So this is a welcome design in my opinion. The one thing I noticed is when you are plugging in a mouse adapter or unplugged mouse adapter, it does cause the application to close, and you have to reopen the oscilloscope, but it only takes about a few seconds. So that is really not a problem in my opinion. And if you don't like the touch screen operation, you can also just disable it by pressing the screen lock. When that is locked, you cannot use your finger to operate the screen. You can definitely still use the mouse and the keypad here. So this is something that when you're in the field, you don't want interference, or you just simply don't want your finger to accidentally touch the screen, you can use the screen lock here. One of the key advantages of this scope is its ability to display signals in intensity grading mode. This capability would allow the scope to display a signal the same way an analog oscilloscope does it. So let me quickly demonstrate that. So now I have the UTG-962E hooked up to the oscilloscope. Let me turn on channel 1 and turn on the modulation. So channel 1 is at 10 MHz, and on top of that I added a 10 kHz 100% amplitude modulation. So let me automatically acquire the signal here. And obviously this time base is not correct, so let me change the time base, reduce it, and you will see the modulated signal. So for that I'm going to change the trigger level just a little bit so we can have a stable signal here. So that looks good, and you can see that the display signal essentially is a color graded signal, which looks very, very nice, just like you would find on an analog oscilloscope. And obviously we can do some fine adjustment as well. So let me pull out the menu. You can see that we are currently in the display of a waveform, and the brightness is at 18%. So by adjust that brightness, you can affect your color grading here. So obviously when I change it to 100%, this is what you would see on a regular scope without the intensity grading capability. And if we further reduce it, you will see that this contrast of your signal started to appear. So this is the capability that we're talking about here. As mentioned earlier, the intensity grading capability is typically only found on some of the more expensive oscilloscopes. Of course, now you can achieve the same thing with the Micsig oscilloscope. Besides intensity grading, this oscilloscope also supports heat map, and let me demonstrate that too. So here I go to Common, and this is actually not very intuitive. The CCT here is actually the color temperature, so that's your heat map, and you can turn it on. You can see that we essentially have a heat map of the signal. Now let me just recenter the signal here, and for this signal you can also adjust it based on the intensity that we did earlier. So let me go back to waveform. You can see now if I adjust the intensity, that heat map is essentially being adjusted. So this is the other capability I wanted to show you. Next, let's use this oscilloscope to generate a Lissajous figure. For that, I'm currently putting in two signals from my 962E waveform generator, and both of the signals are at 1 kHz. And the difference is that they are actually phase shifted by 90 degrees. And now let me change the display to XY mode. You will see that this is the Lissajous figure generated. Now if I start to change the phase difference, we should see the circle changes. So if I change the frequency here, you can also see that we are getting a different Lissajous figure. So of course these are the integer multiples. If I started changing non-integer multiples, you will see that we started to have this kind of unstable Lissajous figure. While we still have these two signals on the scope, let's take a look at the mathematic functions. On this STO1004, the math channel is a channel by itself, so we can enable it here, as you can see that. Now let's take a look at what we got here. So on this mathematics channel, you can essentially do a lot of things. Here we are doing some mathematics of the two waveforms we are displaying on the scope here. So you can see that we can do a addition, we can subtract one waveform from the other, we can do multiplication, which was the signal we're seeing before, and we can do division. So that's actually really powerful. And you can do, of course, between any of these different two sources. So right now we're doing between channel 1 and channel 2. So let's go back here. And of course we can do FFT, we can do even more complex functions. For example, linear algebra between the two channels, AX plus B. So you get an idea. And here we have the advanced mathematics. You have essentially an expression you can define by yourself and utilize the two variables to actually do some cool stuff with the two waveforms that you have. The STO1004 also allows you to save waveforms as your reference waveforms. This comes in handy as you can save a waveform and later on recall it and compare that waveform to the signal you are observing. So let's take a look at that. So for instance, if I come in here, we can go to the Save menu, and this essentially allows you to save that waveform onto disk. I have already saved a couple, but I just want to show you here. So I save that. Of course, you can always name it to a more meaningful name, but right now we'll just use the default out-of-the-box file name here. So once it's saved, you can use the reference button, or you can simply enable the ref channel to recall the waveform. Now you can see that we actually recalled one of the waveforms that we just saved, and we have a bunch. So this one is the one we just saved, and that is actually at the bottom here. You can see there's a little bit of glitch. Actually, I probably just moved it, but nevertheless, that's the waveform we just saved earlier. And you can change the other live waveforms. You can see that the reference waveform did not change. So you get an idea, this reference waveform capability. Next, I wanted to demonstrate the protocol decoding capability of this scope. Right now I'm using an Arduino board, as you can see here, that is generating a serial message. That message is being measured by this oscilloscope, which is hooked up into channel 1 here. Now, of course, we have already acquired a signal, and you can see on the screen that's the output from the UART, and that's a stable signal into channel 1 here. Now, of course, what we want to see is the protocol decoding capability. So for that, I'm going to swipe up. You will see two additional channels, S1 and S2. These are used for protocol decoding. For UART, we only need one of the channels. So let's enable S1. So right now, once it's enabled, let's take a look at the setup. And I have already set it up. It is a UART, you can see here, and receiving channel is channel 1. We have idle high and check bit none. So right now we're in the 8-bit configuration at 9.6 kilobit per second baud rate. And the display is the ASCII that is generated. So let's go back and see what we have on the screen here. So these are some of the things being displayed right now. Now, of course, you can't see very clearly, so let's reacquire the signal. So hopefully the signal is a little bit more dense now. Yep, as you can see, this is the generated signal. Now, for whatever reason, once in a while I do notice that the acquisition actually stops. So right now you can see this actually is not moving anymore. It stopped, but the signal itself is actually not stable. So there may be a little bit of bug somewhere in the firmware. I'm not sure, but I will show you that in just 1 second. So for instance, right now, let's go down here. You can see that we're actually not triggering on any of the data that is available on this message. So right now, if I go back, you will see this indeed becomes unstable again. So I'm not sure why the initial acquisition, after a few waveforms, the waveform stops. But nevertheless, this is actually what the desired behavior. As you can see that the triggering is obviously not triggered at all right now. So what we can do is we know that we have a line carriage return at the very end. So I'm going to trigger on the 0D0A. So either one of them I can trigger. So let's do that. So I come here, I will change the data to equal, instead of AA, I'm going to say 0D. So that's the carriage return. Sorry, that's a line feed. So let's enter, and you can see that we actually now are triggered. and the whole hello world can be seen on the screen here. Obviously, if you zoom it out a little bit, you can see a little bit more. So that actual last question mark there is something that's half of the word cannot be decoded, but it nevertheless is actually decoded correctly here. So if you look at here, we do have the hello world. Now, it is sometimes a little bit finicky to show a specific word, but if you are scrolling through, you do see the entire message being displayed correctly here. So of course, that is just one view of the decoded message. What you can also do is I swipe up. You can see that we have the serial text. So if I press that, you will see the message, decoded message, displayed on the screen here. That's another way for you to see the decoded message. So as you can see here, it is actually very easy to use a scope to decode a signal. As I mentioned earlier, this scope is based on Android operating system. And of course, there are some additional capabilities provided via apps. You can get to the Android interface by pressing the Home button, and there you will see some of the apps that come with the scope. So you can see here we have the user guide that is just a PDF document, and you can scroll through. Now, the resolution on this display is not as good as you would find on a typical tablet. That's because the resolution is only at 800 by 600. Some of the letters appear a little bit blurred. And I'm not able to figure out how to get back to the menu. You would think that this button would be able to get back, but it doesn't work here. So I have to press the Home button again and to get back. That's not a big deal. So you can see that we also have App Market, and that is essentially all the different apps you can install. Currently, there are only 4 of them. The scope itself is the main application. Oh, by the way, there's an update. We'll probably take a look later at what that update is. And then we'll have the WPS Office and ES File Explorer. This one actually I just installed. That actually provides the FTP capability. So when you have your oscilloscope hooked up to your Wi-Fi, you can actually use the FTP interface to access the files on this oscilloscope, which is quite handy. Of course, you can always just plug it in onto a computer via USB, and the drive would show up as an external drive. So that is also pretty easy to use as well. So let's actually get back again, and we'll see all the different apps here. So that's the oscilloscope. This is the electronic tool. You can see we can do some calculations, and that is actually very handy if you are in the field and you don't have a reference book somewhere with you. So this is fairly self-contained. And what else? We also have the gallery. I assume that's the screenshot you have taken. And we have the browser. You know, if you are bored, you can actually use it to browse the internet. We have files. So this is your file manager, and in there you can have the screenshot. Those are all the different screenshots I have taken. And then you have your settings. So the settings, by the way, so through network, you can see that I have already registered my home Wi-Fi. So we can use this oscilloscope, use it as an FTP server, as I mentioned earlier, you can connect your computer to. So we'll take a quick look at that as well. So let me get back. And we have the calculator here. That could definitely come in handy. You notice there's a row of icons here. At first I thought this is for recording, but this is actually not. If you press this, I assume it's actually going back to the main screen here. And this one, some of these are probably only going to work when you are in a different setting here, but nevertheless it works pretty similar to your regular tablet computers. Okay, so I can close like that. So let me just go back to home, and if you swipe up, you will see that there are a few additional applications. And here is the ES File Explorer that I mentioned earlier. This one, essentially, you can use it to set up FTP. And you can turn on your FTP server. Here is the address you can enter on your PC, and you will be linked up to the oscilloscope. So that comes in quite handy. And let's go up here. That's pretty much all the apps that you can find on this oscilloscope here. And if you go to the settings, we can see our current scope is build version 5. It appears I just downloaded a new version, so let's actually upload that version. And hopefully it will have some improvement and some bug fixes. So let me go back here, and if you go to the app market, and I can press the update. Okay, so let's press the install. And it installed relatively quickly. Let me open. Of course, I wouldn't be able to see any difference, but only time would tell if there's anything new. I almost forgot to mention, with this oscilloscope, you not only can take pictures of your oscilloscope screen, but also you can record videos. So to do that, you can just swipe it down, and you will see this button. You press it, you press the start, you can start recording your screen. And whatever you do would be captured in an MP4 format video. So you can later on share with others, rewind and see what you have done. So that is actually useful for educational purpose, and or in the field operation, you see something strange, you can actually record it into a video and later share with your colleagues. Next, I want to get some sense of the actual bandwidth of this oscilloscope. So right now I'm outputting a 10 MHz signal from my HP8642B signal generator, and I adjust the output so that you can see the amplitude is roughly at 1 volts peak to peak, so that I can actually tell when the amplitude drops to 0.707, that is actually the bandwidth. So right now you can see that channel 1, the frequency counter output is at 10 MHz. The input channel impedance of the STO1004 is unfortunately fixed at 1 megohm. So you can see here I used a T and a 50 ohm load to actually terminate the coax signal here. So now I'm going to increase the output from the frequency generator to 100 MHz, and let's take a look at the observed signal here. So as you can see that the amplitude dropped a little bit, so let's readjust and take a look at what we're looking here. So it is roughly, you can see, let me just, oh, this is really imprecise, but roughly you can see that we're at 0.7 volts. So clearly the bandwidth is actually just about at 100 megahertz. Let me reduce the time base a little bit. And you can see the signal is actually very clean, and the frequency counter is showing at 100 megahertz. And just for curiosity, let me increase the output from the HP8642B and see if we can measure frequency any higher than that. So right now we're at 150 megahertz, and you can see this frequency counter certainly won't be able to measure that. Let me go back to 100. Yeah, so it looks like that frequency counter is actually just at 100 megahertz. So that's interesting. So let me turn that counter off, and let's see if we can use, by the way, so sometimes if you swipe the screen, the waveform actually moves with it. So this is just some tweak that they can probably do in the firmware to prevent that from happening. But nevertheless, let's take a look here. So let me actually do another measurement. Let me enable auto measurement. So right now you can see that the frequency is 100 megahertz. So now let me increase that output frequency from the HP8642B. So now let me go to 150 megahertz. And interestingly, this frequency counter, you can see, let me zoom in a little bit, can actually still discern the frequency of the input. So clearly this frequency counter is different than the one that we showed here, because this one you can see that is no longer able to tell the frequency anymore. and this one is at 8893 megahertz, but this one is still showing at 150 megahertz accurately. So these two must be using different mechanism. But let's keep increasing, as right now we can still measure the sinusoidal waveform. Let me keep increasing the frequency, see what we got here. So let me increase it to 200. As you can see that we can still measure that 200 megahertz, which is actually quite impressive. Now, of course, the amplitude of the signal dropped to almost nothing. Let me increase that, see if we can still measure the waveform. Now you can see that there's already some artifacts to the waveform, so we have significant widening of the peaks here. That means that the ADC is actually no longer able to capture the signal accurately. And if I continue to increase the frequency, right now I'm at 220 megahertz, you can see that essentially we're not able to detect that frequency anymore. So 200 megahertz is actually, for all intent and purpose, the maximum frequency you can measure. Of course, there is a significant attenuation on the signal, but nevertheless, you can still make out the sinusoidal signal. So as you can see that even at 200 megahertz, we are still able to measure the signal. So this tells you that this scope at least is capable of measuring signals up to 200 megahertz. At least the digital portion is more than capable, whereas the analog portion obviously has a bandwidth of just at around 100 megahertz, as we saw earlier. Of course, remember right now we're at the 1 gigasamples per second. That's a single channel performance. So let me enable channel 2, see what we got on channel 1 here. As you can see that as soon as we enable channel 2, we no longer able to measure the signal. That is actually a 200 megahertz signal, so this is to be expected. So let me change the signal back to 100 megahertz. And of course, let me readjust the signal so that it sits within that range here that we showed you earlier. Now let me turn on channel 2. And you can see that there's not a whole lot of difference between the captured signal here. So now let me enable channel 2 and let me increase the output frequency and see. Oh wow, so right now it decreased quite significantly. See, we're at 150 megahertz, and so right now it's at 150, 160. We're not able to see that signal anymore. So let's keep it at 100 megahertz. And now let me enable channel 3. So this would further drop the sampling rate to 250 megasamples per second. You can see here. So this is essentially 1/4 of the sampling rate. And at 100 megahertz, we're seeing the signal still pretty good. So let's increase the frequency again. 110, 120, yeah, you can see that at 120 megahertz, we're not able to measure the signal correctly anymore. And this is to be expected, as right now we are only having a 250 megasamples per second sampling rate. So let me reduce it back to 100 megahertz. And now let me turn off some of the channels. Turn off channel 2, and you can see that the sampling rate increased back to 500 megasamples per second. And let me turn off channel 3 as well. So now we go back to 1 gigasamples per second. One thing I noticed is that actually when you have the other channels off, sometimes you, for example, forgot the trigger. So let's just say the trigger source right now is set to, in this case, is I think it's channel 2. And in this case, right, so the signal obviously won't be able to trigger. But if you look at the sampling rate here, it also decreased to 500 megasamples per second, even though we only have channel 1 now. So I'm not entirely sure how this is done, because you have the channel 2 triggering. That means channel 2 is active, but right now channel 2 is not. So this to me may be an oversight in terms of the firmware, not entirely sure. But anyway, that's something when I first saw, I thought it was odd, but quickly realized that's because the channel source was not set correctly. So right now, if I change the channel source back to channel 1, you can see that again we have the 1 gig samples per second sampling rate up there. For the last experiment, I wanted to use this Avalanche pulse generator to measure the rise time of the scope. According to the specification, it is rated at 3.5 nanoseconds. So let's take a look at actually what we can measure here. Right now you can see that the Avalanche pulse generator is hooked up to the channel 1 input via this very short BNC cable. Now I'm going to turn on the pulse generator here. And you can see that the update rate is very fast on this scope. Let me try to auto-acquire the signal to see if we can get that. I don't think you can. Yep, you can. So you can see that this signal is actually very, very narrow. And let me manually change that to see if we can. Yep, now we can see this is the pulse captured on this oscilloscope. So let me actually put it down a little bit. And let me increase the amplitude here. So this is good enough for us to do the measurement. Let me make it wider. And so now let's measure the rise time here. So for that, we're going to use both cursors. I'm going to use this cursor to get it roughly to about 75%, so probably here. And then we're going to use the other cursor to measure the time in between. And you can see the delta is about here 2.5 nanoseconds. So that's clearly a very fast rise pulse here, and definitely within the limit specified by the specification, which is 3.5 nanoseconds. So clearly it can achieve the fast rise time required for the 100 megahertz bandwidth. Now, it will be interesting to see if I turn on channel 2 what this signal looks like. As you can see that as soon as I turn on channel 2, it seems like the signal expanded a little bit. So let me try channel 3. Yeah, as soon as I turn on channel 3, this pulse becomes a little bit of a wobbly here. So we're actually not able to fully capture the pulse cleanly. So that means that definitely there's a reduced bandwidth. But from 1 gig sample per second to 500 meg samples per second, you can see that the change is relatively subtle here. And that's pretty much what I wanted to cover in this video. If there is something else you wanted me to comment on this oscilloscope, please let me know in the comment below. There are a few issues here and there as I went through the review, but overall it is a very capable and well-designed oscilloscope, and I guarantee that you will like it as well. Anyway, I hope you enjoyed the video. If you liked the video, please don't forget to give it a big thumbs up and remember to subscribe to the channel for more videos like this in the future. I will catch up with you next time.